Hello and welcome to our video where we are going to see example for backpropagation. In our previous videos we have seen theory for it. Let us do it with the help of an example. As you can see, a neural network has been given to you. Okay, our aim is to train neural network. What do you mean by that? Already weights, you can see nodes are there, right? This is input layer, this is the hidden layer, and this is the output layer. Okay, so you can see there are various arcs. Okay, it is a fully connected network. So on this arcs, these arcs are labeled with the help of weights. Fine. So these weights we have taken randomly. So initial weights, what you have to take, those are going to be your random weights. You also have the bias value. Okay, so one bias is supplied to hidden layer and the other one is supplied to the output layer. Okay, and bias is also labeled as 0.5. Okay, and these weights, whatever are done, these are randomly weighted. Okay, random weights we have provided to them. And three inputs are also given to you. The input is fixed, right? So x1 is 1, x2 is 4, and x3 is 5. These three inputs are given to us. What is our aim is, what are we going to do first of all? As we've seen in algorithm, weights we have been given, right? Inputs we already have. Now using this, we are going to propagate data to the next layer. Okay, we are going to propagate data to this layer, and using its output we are going to propagate data to the last layer. So once we propagate data in forward fashion, then we have to propagate data in backward fashion. Okay, because at this point we are going to compute the error. Okay, so the errors are more, we need to reduce our error. Our aim is to reduce this error. So in order to reduce this error, we need to propagate data in this fashion till we reach the input layer. Okay, again we have to go ahead, again we have to come back. This is nothing but backpropagation algorithm. We have to continue this till our error becomes minimal. Okay, so let us see with the help of example how to do this. So initially what I have to do is, I have to first of all compute input for this. Okay, hidden node will get input from x1, from x2, and from x3. Input to x1, x2, x3 is fixed. As I said, input to x1 is 1, input to x2 is 4, and input to x3 is 5. Okay, now I want to compute input to h1. How to compute that input? This is our question, right? So how to compute the input is, multiply the value of this input with this weight, right? So it will be x1 into w1 plus, because only one input is not given to h1, the second input given to h1 is from x2, right? So it will be x2 plus w3 plus the third input will be x3 plus w5. So all these three input plus, you can see bias is also input, so b1 also will be added. So in this fashion, when you do this calculation, you get the value for input of h1, which I denote it using zh1. Okay, so as I said, w1 x1 plus x2 into w3 plus x3 into w5 plus b1. Okay, so when you substitute all the values, all values are provided to you as shown in the above diagram. Okay, so when we substitute, we get the final value for zh1. So what I'm using the values term zh1 to denote the input to this h1. Okay, so that is my first point. Secondly, I have computed input to this h1. Now I'll compute output of this h1. So that means what I have to do is, I have to apply activation function to this h1. Okay, we've learnt about activation function. We use sigmoid activation function. Sigmoid is nothing but 1 upon 1 plus e raised to minus zh1. Okay, you have to do this particular calculation. Now, what is the value of your zh1? 4.3. So substituting that value over here, okay, you have to use a mathematical calculator. You can either use online. So this is the value what you get. So this value, so how did you get it? You applied sigmoid function or the activation function to zh1 and you got this value, that is nothing but your h1. Okay, this is going to be outputted from here. So you got the actual value of h1, what do you call output of this h1. Okay, so it is 0.986. So you have worked with h1. Now you'll work with h2. Similarly for h2, what you have to do? Find out the input and find out the output. I'll repeat. Find out the input in the sense, what are the incoming node for h2? x1. So I'll take x1 into labeled arc is w2. x1 into w2 plus x2 into w4 plus x3 into w6 plus again bias 1 is coming. Okay, so plus bias 1. So when you do this plus bias 1, when you do this you get ZH2. So put all the values. Again you get the answer as 5.3, but that is input ZH2, right? I have denote input by ZH2. Now to input, again I need to apply the this function, what? Sigmoid function. So after applying sigmoid or the activation function as same 1 upon 1 plus e raised to minus ZH2, okay, that is e raised to minus 5.3, I get the value as 0.9550. So that is the value for output of this. Okay, thirdly, now I have computed input for this, output for this, input for this, output for this. So we have done with this layer. Okay, no more nodes are there. Now we need to go to the last layer, that is your output layer. Okay, so in which fashion we are proceeding? We are proceeding in forward fashion, feed forward fashion. Now what is there in this layer? Again I have input and I have to find out the output. Okay, let us work on input first of all. So the input I denote it using Z01. Okay, so again, which are the incoming nodes? This one and this one. So my output will be input will be H1 into W1 plus H2 into W9. Okay, plus I also need to add the bias to values. So you can see over here, same thing is represented over here. As I said, I put the values and calculate your input. Okay, now this is Z01, that is your input. Again apply the activation function. So it is, you need to apply the activation function, you get the value 0.8896. Okay, same, in the same fashion you are applying the activation function. So you get the value for Z01. You apply activation function to your input Z01, you get the output. Output I denoted by O1. So I got the O1. Similarly, I want to get O2. So how will you find O2? It's that simple. H1 into W8 plus H2 into W10 plus the second bias value. Again, you will get the value for ZO2. Apply the this function, activation function. Each time you have to apply sigmoid only. Okay, same function. So apply sigmoid function. So after applying sigmoid to ZO2, you get the answer for O2. Okay. So as we have discussed about ZO2, that is input to it, and finally output of that O2. Okay. After this, we have reached to our final layer. We started from input layer, we went to hidden layer, and we have found input and output for both output layer also. Now we want to calculate error. See, what we had done for our network is we had assumed weights, right? We had assumed weights, but there is certain target that we expect. That why we are doing this. So we want O1 should have certain target output and O2 should have certain target output. That certain target output is represented with the help of T1 for O1 and T2 for output layer 2. Okay, output node 2. So this is what you expect and this is what you expect with respect to second neuron. So this is what you have got. Okay, you have found, like when you traversed, right, we have found O1 and O2. So this is the value of O1 which you have computed, what you have done right now till now, and O2 what you have computed. So O1 minus the desired value of T1, this is my expected value for the network, and O2 minus desired value of T2. So what I need to do is I need to find error. Error is found in this fashion. Okay, so after doing this you get certain value of error. Okay, you get a certain value of the error. So this error is large. It has to be closer to 0, very close to 0, and our aim is to reduce this type of error. Okay, so that in order to reduce this error we are using backpropagation. Okay, so we use the concept of gradient descent. Before going further, I would like to introduce here how to do this. We do it using the concept of gradient descent. Okay, so let us see what is the concept of gradient descent. So as you can see over here, I've drawn a small graph. Now, suppose, let us imagine that we are over here. Okay, what is plotted against what weight is there? Okay, now here here we assume that this is our error function. Okay, this is our error function. Right now, I got error over here. Okay, suppose we are at this stage and this is the error function at our current point. So what we are going to do is, as I said, I introduced a term, we are going to perform gradient descent. Okay, gradient means what? Slope. Okay, descent means what? You have to come down. Okay, it is very long theory, but here I'll be explaining in short. So what we need to do is we need to take differentiation. Okay, differentiation of function is performed. Fine. So slope will give us the direction whether we want to go upward or we want to go downward. Like differentiation of this function will be performed, whatever is the function over here. So its slope will give us the value that we want to go upward, that is the values of the parameters. How to update those parameters, whether I should increase the value of parameter or whether I should decrease the value of parameter. This I'll be understanding using the slope of this function. So I have to find the slope just by differentiation of function. So what we have to do is we have to go for differentiation operation, right? So gradient descent helps to update the weight. Okay, we are going to update weight. Our aim is update weight in backward fashion by maintaining minimum error function. So it will help us do this. It will control on error function. How? By reducing the weight. So by how much to reduce weight? That is also the quantity. Suppose weight is 1.0. So by how much to reduce weight? By reduce it by 0.5 or by 0.3. This will be decided by this gradient descent. So the point is we have to perform gradient descent. So as I said, we have to go for differentiation, or you can call it as partial derivatives. So here we introduce the term partial derivatives. Okay. So if for the same example, for the error function, if I ask you go for partial derivative with respect to O1, how will you do it? Is derivative of error with respect to O1. Okay, derivative of error with respect to O1. How will you go for it? It is nothing but 1 half, this 2 will come out. Okay, so 2 by 2 it gets cancelled, O1 in O1 minus T1, and this term will become 0. So what is your answer? Your answer is O1 minus T1. This is what you have done for with derivative of E with respect to O1. Now find out the derivative of E with respect to O2. Okay, so how we are going to do is derivative E with respect to O2 is again this 2 will come out, 2 and 2 gets cancelled, O2 minus T2. This term will become 0. Okay, because it is with respect to O2. So in this fashion you have to compute derivative. Okay, now see what has happened. You have found certain error, right? And now you want to minimize that error, right? So in order to minimize error, you're using gradient descent. Gradient descent uses partial derivatives. Okay, now with what are you going to work? Okay, so the point is you want to check, like you have computed error, you have come to the output layer, you have computed the error, you want to go backward, right? So while going backward, you want to update weights for each and every layer, right? So now you are at output layer. Initially you will go to, when you're going backward, you will come to the hidden layer. So the moment when you come to the hidden layer, what weights will be modified? So when I start from output layer, I want to come back. Okay, I want to go to hidden layer. So what weights I want to modify? I want to modify W7, W8, W9, W10 with respect to the error function. Okay, so what I have to do initially is with respect to error function, I have to compute derivatives for all these functions. That is dE by with respect to W7, dE with respect to W8. So dE by dW7, dE by dW8, dE by dW9, and dE by dW10, and dE by bias also, because bias also affects error. So initially I'll be computing this. So I'll reach here and then we will also compute this. So let us first of all see how to compute this partial derivative. So I have to compute dE by dW7. I'll mark over here. This is the first thing we are going to compute. And this what is given over here is nothing but we have removed certain derivatives. We've computed certain derivatives which we are going to require further. Okay. So just certain rough work or will give you idea of derivative. So this formula we have previously seen. Okay. If you have diagram in front of you, you can compute this. This formula we have previously seen. We have calculated also how to find Z01, that is input to O1 function. Now I want to find its derivative with respect to W7. So the moment when I find its derivative with respect to W7, what happens? This all becomes 0. Okay, W7 cancels. So what is my answer? H1. Okay, if I want to find its derivative, so here is the answer. If I want to find its derivative with respect to W9, so this gets cancelled, my answer is going to be H2. So here I get. If I want to find its derivative with respect to B2, okay, because B2 also I'll be needing, right? So dz01 by db2, this all gets cancelled, my answer is going to be 1. B2 and B2 gets cancelled, 1 is going to be my answer. So here you can see. Similarly, you have Z02, formula for Z02. So derivative of Z02 with respect to W8, W8 gets cancelled, your answer is H1. With respect to W10, W10 gets cancelled, right? This is 0, this is 0, answer is H2. And with respect to B2, this all gets cancelled, this and this, so answer is 1. So you can see 1. Okay. So this is what we are going to need further. It was just an idea for derivative. So what is first thing we are going to compute? The effect of error on W7. okay, because I want to modify W7 as we've seen previously. So let us see how to do DE with respect to W7. So we are using the famous chain rule over here. Okay, now see, when I go to compute DE, okay, now further, okay, the computation of these things I'll be telling in the next video. We'll continue from here. Okay, thank you for now.